Good morning, everybody. Welcome to overcast and sort of rainy Tuesday morning of Chem 11:05 with your host, me, Dr. White. All right, got a fun-filled morning ahead of us, but there are a couple things I want to talk about. The first thing is, I think about a year ago, maybe less, COD started something called quarter term grades. And I had to get them in over the weekend, which I don't know if you saw them or not. Just ignore them. It's only based on test one. And I use the 90, 80, 70, 60, and so on, like in my syllabus, to give you your grade just based on test one. And that's just something all faculty have to do in terms of entering those grades, and I did. But as I said on Monday, yesterday, all of you still have a chance to get an A, because if you didn't do good on test one, that will be your drop one. All right, that's the first thing. Second thing I should have mentioned yesterday, and that is some of you don't know how to use this yet. Not today, but either in my office hour tomorrow or next Tuesday after lab. If you don't know how to use a scientific notation calculator, stick around. I'll teach you again. I'll work one-on-one with you. Because if you don't, you're not going to do good on test 2, 3, 4, or the final. No, let's call it the final. So if you don't know how to use this with scientific notation, please make sure you see me for help. Now, one of the things, one of your colleagues after class yesterday asked a question, and you can ask questions in class too. And your colleague thought, for some reason, your colleague's answer on the same calculator was different than mine. Now, number one, I do make mistakes. And if you think I made a mistake, let me know. I will be grateful, not that I made a mistake, but you let me know so I can correct it. I am not perfect, never will be, never have been. I try and do everything correctly, but mistakes happen. Now, it turned out your colleague had the same calculator, except instead of having it in scientific notation, it was in what's called flow, and gave the wrong answer. As soon as your colleague, I showed your colleague how to change it to flow, from flow to scientific notation, it worked perfectly. So again, if you don't know how to set this up in scientific notation and use it to multiply sign or divide scientific notation, see me either tomorrow night, office hours, or next Tuesday after lab. All right. I promised I'd go through the practice problem set 4. Thumbs up, people. Everybody, oops, wrong thing. Let me just move this down here. Everybody see chapter 4 practice problems on your screen? Thank you. All right, let's go through it. Draw the Lewis structure for the following. Lewis structure shows valence electrons. Look at the periodic table at the top of the column, and for an element that shows you how many valence electrons it has, and you put one dot on the side before doubling up for an element. And for hydrogen, one valence electron, and it could be on any side. Same thing, sodium, calcium. 2 of the sides have dots, 1 dot, and 1 has 2 of the sides have no dots. Now, common mistake, and let's go for carbon, 4 valence electrons. And you'd put 1 dot on a side before doubling up. for an element. This is wrong because you have a doubling up right here before you have each side has a single valence electron. So make sure you don't do that because I'll mark it wrong every day of the week. Now, oxygen, organic chemists like to put the paired electrons top and bottom, but there are other variations of this. Two sides have two dots, two sides have one dot, because oxygen has 6 valence electrons. And there's iodine. All right, now, what ion does the following element form? How do you do that? Let's do oxygen. And before we do that, I have to open up my green periodic table. All right, now, if we look at oxygen to find out what ion it will form, oxygen is at atomic number 6. And what's the nearest noble gas numerically based on atomic number? And that's neon at 10. Helium is 6 away, neon is 2 away, argon is 10 away. So neon is the closest. So how do you do this? You have oxygen, 8 electrons, 8 protons. It wants to have the same number of electrons as the nearest noble gas, and therefore that's 10 electrons. It will not change the protons. Each electron is a -1. Each proton, that looks better, not really, is a +1. Multiply them, -10 plus 8. This becomes a -2. How do you show the ion? Chemical symbol, upper superscript to the right, either -2 or the newer way, which I don't like, 2-. Either one would be correct on the test. So again, you find out how many electrons and protons, you find out how many electrons the nearest noble gas has, in this case 10. Each electron is a -1 charge, each proton is a +1, and you get the numbers, add them up, and the symbol and the charge. And that's how you do the charge. And why don't you do the following? What charge does calcium have? What ion does calcium have? Your turn. In case you don't know, calcium is Ca. All right, I think everybody's done. So let's do it. Now, if we look at calcium, it's at 20. The nearest noble gas, you have two choices. Argon, 2 away. Krypton, 16 away, which is a smaller number. Hopefully I'll pick 2. So it's at 20, wants to go to 18. What does that mean? Oh, let me be consistent. Doesn't matter what you put on top, but guess what? Got my numbers mixed up. Let's start this again. It's at 18. I did it again. Got it right. It's at 20 electrons, 20 protons. It wants to go to nearest noble gas, which has 18 electrons, 18 protons. Each, this will be still 20. Each electron is a -1. Each proton is a +1. -18 plus 20. And you add it up, it's a +2. How do you show the ion? This way or this way. This is the older way, which I like. I guess I'm old-fashioned in this. And if you remember, I think I told you that all right, Ruben, I'm not sure about the mortar in the lake. I'll have to ask you about that during the break. All right, now, if you know, everybody tells you, medical science tells us we have to have calcium in our diet so we have strong bones and you don't get certain diseases like osteoporosis when you get older, like me, which I don't have, thank God. But anyways, they're not talking about calcium, the element, because it's a metal, just like gold or silver or copper. You're not going to be chewing on that, and your stomach really can't digest it well. They're talking about calcium cation +2, which does make your bones stronger. And I do take a calcium supplement, so I don't drink milk anymore, which is also fortified with calcium supplement. All right. Let's move on. Now, the question is, what's the empirical formula for a molecule with the following ions? All molecules have a net zero charge. So how do you do this? Well, let's look at C. I keep on forgetting, not all of you read cursive. So how do we do this? What's the empirical formula? The simplest formula with lithium +1 and oxygen -2. Well, this is a +1 charge, and this is a -2. And they have to add up to 0. They don't. We can't change the charge, but you can change how many. If I had 2 lithium, that'd be +2, 1 oxygen -2. It does add up to 0. So how do we show that? 2 lithium, 1 oxygen. And why don't you try this one on your own? What would be the empirical formula for a molecule of calcium +2 and nitrate -1? When you have more of a polyatomic ion, you put it in brackets or parens, yep. All right, is everybody done? I'll give you another 15.5 seconds. Go. I'm watching a clock now. Give you another bonus 5 seconds. Time's up. All right, this is a +2. This is a -1. It must add up to 0. Oh, it doesn't. How do you get this to be a -2? You can't change the charge, but I can have 2 of them. And how do I show that? 1 calcium, but since this is a polyatomic ion, poly meaning more than 1 element in that ion, I put it in brackets, and then subscript to the right, I put it 2. And that's how you do these. And you should know how to do these, because you already know why I call these practice problems. If you notice, I got it right. Yay. Now, let's talk about drawing the Lewis structures for molecules that have covalent bonds. And by the way, you should know what an ionic bond is. Transfer 1 or more electrons from one atom or group of atoms to another atom or group of atoms. You should know what a covalent bond is, and that's sharing, that's the important part, of pairs, that's important too, of electrons between 2 atoms. And as with ionic, covalent atoms of elements want to have octet 8 valence electrons. And the exception is hydrogen, and that's 2 valence electrons is its octet. Now, I do want to remind you, when it comes to covalent bonds, there are 3 covalent bonds or types of covalent bonds. And you should know the first one is a single bond. And it's 1 pair of electrons, double bond, 2 pair, and finally, triple bond, 3 pairs. So single bond, 1 pair of electron, double bond, 2 pair, triple bond, 3 pair. So when you want to look at something like what molecule hydrochloric acid, first of all, you have to find out from the periodic table, hydrogen has 1 valence electron, chlorine has 7 valence electrons. And the hydrogen has 1. The chlorine has 7. And notice it has 1 unbonded electron, and hydrogen has, and it says, I've got 1, you've got 1, let's share. And this is the Lewis structure for hydrochloric acid, HCl. And what kind of bond holds the hydrogen and chlorine together? 1 pair of electrons. Oh, look, someone was nice enough to write this nice table on my whiteboard, and that's a single bond. Now for nitrogen, each nitrogen has 5 valence electrons. And notice this nitrogen says, I've got 3 unpaired electrons. You've got 3 unpaired electrons. Let's share. And unlike an element in a molecule, you can have more than 2 dots on a side. And this would be the structure, or the Lewis structure for nitrogen gas, which is what you're inhaling now, along with the oxygen in the air. And I would ask you, what type of bond holds the 2 nitrogen atoms together in nitrogen gas? Hint, hint. And the answer is 3 pairs of electrons. Remember, a pair is 2. That's a triple bond. Know something? I've got to share the fun. O2, oxygen gas. Each oxygen has 6 valence electrons. Why don't you try drawing the structure, the Lewis structure for oxygen gas? Your turn. And when you're done, give me a thumbs up. Let's try that way, see how it works. I'm seeing a lot of thumbs coming up, but let's take another 20 seconds to finish up. That probably was 20 seconds, so let's go. Each oxygen has 6 valence electrons. Now, what I'm doing now, you don't have to do on a test, but I'm trying to show you. And this oxygen says, I've got 2 unpaired electrons. You've got 2 unpaired electrons. Let's share. And they do. Now, the non-bonding electrons come along for the ride. And that's how you do it. And what kind of bond holds 2 oxygen atoms together in oxygen gas? Oh, 2 pair of electrons. It's a, as Spence is killing me, a double bond. And Ruben, I think I remember what you're talking about. I'll probably do that, talk about, remind me tomorrow. And at the end of class tomorrow, I'll talk about that. It's actually not a mortar. If you can tell me which review, let me know. I'd be interested in reading it. It's a good story from high school. My high school stories are chemical in nature. Yes, I wanted to be a chemist back then. All right, let's move on. Now, let's look at H, sodium hydroxide. How do you draw the Lewis structure for that? Now, sodium hydroxide. Sodium has 1 valence electron, oxygen 6 valence electrons, and hydrogen 1 valence electron. Remember, look at the top of the column of the periodic table. Now, listen carefully. This is important. All alkali metals and all alkaline earth metals always form ions. They never, ever are involved in a covalent bond. I've asked chemist friends of mine for years now, do you know an example of them being in a covalent bond? And nobody has ever come up with an example because it just doesn't exist. So remember, this always forms an ion. And what ion does it form? Na+. You can figure that out or remember it. So let's take a look at how you do this. Oxygen has 6 valence electrons and hydrogen 1. And we have this sodium plus. This oxygen says to the hydrogen, I've got an unpaired electron, you've got an unpaired electron, let's share. And they do. All right, someone have a question? Or someone have their mic on? Spencer, do you have a question? I'll mute your mic. If you have a question, feel free to ask. All right. Now, sodium forms a plus cation, so it's got an octet. It's got the nearest noble gas. Now, if we look at this, and I'm going to go Technicolor on you, hydrogen has 2 valence electrons. It's sharing it. And it's got its octet. Remember, hydrogen octet is 2. Now, oxygen has its, it only has 2, 4, 6, 7. What do we do? Well, let's go back up here and notice sodium has 1 valence electron, which it gave up to get the sodium cation. And where does that electron go? It goes to oxygen here. And this now forms a polyatomic ion. It has an extra electron. Therefore, this whole thing, hydroxide, OH minus. And if we look at sodium hydroxide, this is the Lewis structure. You have an ionic bond between the sodium and the hydroxide anion, polyatomic anion, and between the hydrogen and oxygen is a covalent bond, single bond. And that's how you do polyatomic ions. I'd highly recommend you practice that. And if you remember, what are the 3 types of covalent bonds? Single bond, 1 pair of electrons, double bond, 2 pair, triple bond, 3 pair. And with that, we're done with the problem set. Any questions on chapter 4 problems? Going once, going twice. So we're done with that. All right, what I'd like to do now, and for a while, is go back to what we were talking about on Monday, yesterday. And first of all, let me open up something. Actually, two somethings. All right, thumbs up, people. Do you all see test 2 important information on your screen? Thank you. Now, this will be given to you. You should know. Let's You should know 1 mole of an element equals Avogadro's number of atoms of that element. 1 mole of a compound, such as water, equals Avogadro's molecules, 6.02 times 10 to the third molecules of that compound. The past students have to memorize this. I will be giving this to you. So let's do a little practice. And why don't you try this one? I'm going to let you try this. I'm going to be back in a minute. I got to go blow my nose because I haven't been feeling well. You try All right, time's up. Let's do this. What are we being asked to find? How many, whoops. Let's try this again. What are we being asked to find? How many molecules of water? What are we given? We're given 5.987 moles of water. And it's time to figure out, what do we do? Well, this is the only number we have to start with, so I will. And don't forget to put the units down. And now it's time to use your good buddy, your good friend, unit analysis. I love that whistle. Unfortunately, the company that makes it went out of business. I've got 4 of them, and they will never leave my house. So, how do we get from moles of water to molecules of water? Well, if we had a ratio conversion, what units do I want my answer to be? Molecules of water. And now this is how you use unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of, unit-wise, goes underneath the ratio. So I'll put this molecules of water and moles of water. Now, where do I get these numbers? Well, remember, if you have something equal to something else, you have 2 ratios, A over B and B over A. So do I have a relationship of moles equal molecules of water? And the answer is yes, you do. If you look at important information, 1 mole of a compound equals Avogadro's number of molecules of that compound. So 1 mole of water equals 6.02 times 10 to the 23rd molecules of that compound. So for every 1 mole, oops, I didn't want to do it in red, I have 6.02 times 10 to the 23rd molecules of water. Now, anything divided by itself equals 1, meaning cancels out. Notice I have moles of water divided by moles of water. This cancels out. The only thing I'm left with unit-wise is molecules of water, which is what I want my answer units to be in. So now I'll pick up my calculator, turn it on, clear it. It's in scientific notation, 5.987 times 6.02, blue key, double E, 23, hit enter. And my calculator gives me this number. Times 10 to the 24th. But on test 2, like on test 1, it will say, please use proper significant figures for all calculated answers. This is 4 significant figures. Avogadro's number is a calculated number, and this is 3 significant figures. I once found on a website, I don't know who would need it, but obviously somebody did, and it was reputable. I think they had Avogadro's number to 20 significant figures. In my class, we used 3. When you multiply and divide, by the way, 1 is an exact number and plays no role in the calculation. or I should say in determining significant figures. So 4, 3, which is the lower number. Hopefully you pick 3, round this off to 3, keep the 3, keep the 6, keep the 4, use the, or 0, use the 4 to round off. That's 4 or less, drop that. So the correct answer is this 3.60 times 10 to the 24th molecules of water. Let's do one more. That's weird. And why don't you try this one? How many moles of mercury, Hg, are in 7.81 times 10 to the 33rd atoms of Hg mercury? Your turn. I just thought of something. This is a public message to Ruben. Hi, Ruben. Tomorrow, beginning of class, remind me and just say the word brainiac. Okay? Remind me brainiac, and I'll tell you that story to you and the whole class. And I'll also have a special video for you to watch. So it'll be lots of fun. And if Ruben doesn't do it, because the rest of you remind me, beginning of class, just say brainiac. I'll know exactly what you're talking about. One thing I should have done to help you out let me clean this up a little. And to help you out, 1 mole of an element equals Avogadro's atoms of that element. 1 mole of an element, Avogadro's number is 6.02 times 10 to the 23rd. I think just about everybody's done. So before we get back to this, I'm talking about Avogadro's number. I think I might have told you this, but I should tell you again. First of all, my birthday is the end of December, so you got plenty of time to save. My all-time favorite birthday gift would be a mole of pennies. Only a mole of pennies, that'd be 6.02 times 10 to the 23rd. If you do the math, that's 100 million piles of pennies. Each pile has $1 billion in pennies. If you want to write me a check for that, you can too. And that probably is all the money that was, is, and will be on this planet in dollars. It's just a mole of pennies. All right, let's get to work. Question is, how many moles of mercury? So what are we trying to find? The right color ink. How many moles of mercury? What are you given? 7.81 times 10 to the 33rd atoms of mercury. And therefore, once we do this, you don't have to look at this again. And this is the only thing we have to start with. So I'm going to start with that number. What units do we want our answer to be? Well, we figured that out. Moles of mercury. And if we had some ratio, let's see if I can get a better straight line. That's better. What would go on that ratio? Well, it's time to use your good buddy, your good friend, unit analysis. Whatever we're trying to get to, the units go on top of that ratio. Whatever we're trying to get rid of, the units go underneath. And let's write the units on that ratio. And where do I get these numbers? Where do I have a relationship between moles of mercury or any element and atoms of that element? If you look at important information, 1 mole of an element equals Avogadro's number, 6.02 times 10 to the 23rd atoms of that element. So I know for every 1 mole of an element, there's 6.02 times 10 to the 23rd. Now, before I pick up my calculator, I'm going to check my units. Notice atoms of mercury divided by atoms of mercury. And anything divided by itself equals 1, meaning that cancels out. And I'm left with this. And now I can pick up my calculator. But before I do that, what I'd like to do is show you how unit analysis shows you made a mistake. What if you set it up this way? By the way, it's wrong, but how do you know it's wrong? And say you use the ratio this. How do you know this is wrong? Because when you do the multiplication, you have atoms, just the units, forget about the numbers, times atoms of mercury divided by moles of mercury. And that would be the units of your answer, which is not what we want. Nothing cancels out. And this is how you tell you've done it wrong and you set this up wrong. This way, with the red arrows, shows me this cancels out with this. I may get the right units. So yeah, So now we know we're going to get the right answer. And with that, clear my calculator. And my calculator gives me the following number. Let me make a little room here. Now, this is 3 significant figures, exact number, 3 significant figures. Therefore, my answer should be 3 significant figures. Keep the 1, keep the 2, keep the 9. Use the 7 to round off. That's 5 or higher. Drop that, increase this by 1. Ooh, when you have 1.29 and you want to increase that by 1, let me just give myself, how do you do that? 1.30 times 10 to the 10th moles of mercury. And that would be your answer. Now, important thing for test 2, listen carefully. And that is the following. Show your work. If you had made a mistake on your calculator, put in the wrong numbers and got a totally different number, but you showed me you set it up, and if it was 5 or 6 points, I'd take off 1 point for a math error. If you don't show your work and you made the same, I pushed the wrong buttons when I was doing my math, my calculator, I give you 0 points. So it always pays to show your work for a problem on my test. And that's one of the main reasons I don't do multiple choice, because if it was A, B, C, and D, and you put the wrong numbers in, you're going to pick the wrong one, and you get 0 points, even though you know how to do the problem. So it pays to show your work. And with that, I looked at the clock. Let's take a 5-minute break, and we're going to come back and do a really exciting lab. Trust me, I'm a chemist. Did that work? How about trust me, I'm a doctor. Did that work? Trust me, I'm a chemical doctor, organic chemical doctor. It's going to be fun. I'll see you in 10:05. Let's get back. Oh, I'm running late. I'm late. I'm late for a very important date. You know where that comes from. Let's get going. All right, it's lab time. And let me just close a few things here. And then let me open up the lab. All right, hold on. And today's lab is moving electrons from shell to shell, also known as the flame test. Now, as you know, all elements have atoms, and the atoms in the center are in the nucleus are the protons and neutrons. And all around the nucleus are the electrons in the subshells of shells. Now, what happens if you take an electron, say this one, and you give it energy and you move it to another subshell, higher one? Well, now it has more energy and it's up here at a higher subshell where it doesn't want to be. As soon as you take that energy away, it goes zoop right back to the old subshell it was. And when it comes back down, it goes zoop. Is that a word in English language or others? I just made it up. Zoop. It gives off the energy that you gave to go up to the higher subshell. And you can see that. How can you see energy? You can see the energy given off when the electrons move back to their original shells. And like I say, there's specific distance in the shells and they stay in a certain shell, but when you add energy, they go to another one. And when this happens, when they go back to the original shell, they lose their energy, and one form of energy is light. And different electrons give off different amounts of energy, which when they return to their shells, which means you'll see different kinds of light being given off, the colors. And how can you see that? Thumbs up, people. Everybody see YouTube on your 4th of July? Was that fun or was that fun? I love fireworks. And when you see fireworks going off, the different colors, highlight that, different colors you see are electrons moving from shell to shell. When the fireworks explodes, it gives off a lot of heat, energy. And that energy causes the compounds that are also in the fireworks shell, and Dr. White is not a fireworks expert, but to move from shell to shell. And then when they move a little farther away from the energy, they say, oh, there's no energy. They go back and they give off that beautiful colors. And I love fireworks. By the way, do I have time? I do. Back when I was your age, oh, that was a long time ago, before Chicago paired the fireworks with the orchestra. I don't like that. If I'm going to watch fireworks, I just want to see fireworks. I don't want to hear music with it. It ruins the whole thing for me personally. That's my personal opinion. But back a long time ago, I and a couple of my friends, a long time ago, and they were all small like me. No, I'm not small. I'm 6 foot and big. We used to go to the lakefront in Chicago and watch the fireworks. We always got good spots because 4 big guys, nobody's, we're going to stand there. Okay. And I didn't say that, but oh, I love seeing that. And where I live now, they've got nice fireworks, and all I have to do is go sit out my front lawn on the 4th of July because where they have it is close enough and it's up in the sky. I can see it. I don't even have to go to a crowd, which is a good thing now that I've gotten older. All right, let's look at today's lab. And here I have a couple showing when you heat up a chemical, certain chemicals, and this is mainly ionic compounds, we have what's called a flame test, and it gives off a characteristic color. And these flame tests are when the atoms, electrons in the atoms of that element move from shell to shell and then go back again. Let's take a look at one of these real quick. And you can go back at your leisure. And this is copper cations.
We're going to do a flame test on a number of selected compounds, primarily group 1 and 2 ions. And these are aqueous solutions, and we have just a inert metal loop. We're going to dip the end into the solution and put it into the flame.
Ooh.
And that excitation characteristic color is like a fingerprint for an element. So we're going to look at a number, and then we're going to ask you to identify some unknowns. Potassium. It should be a lavender. This is barium. The green. This is calcium. Calcium. So the yellow red. Strontium.
This is my favorite. Do it again.
Lithium.
All right. So if you notice, when you put different chemicals into a flame, certain chemicals, ionic compounds, they give off different colors. And as the video showed, they're almost like a fingerprint. And they're used in the old days to identify certain compounds. Now, in an ionic compound, you have cations, plus charge, and anions. minus charge. And like in sodium chloride, NaCl, please pass the NaCl, which causes the color? Is it the cation or the anion? By the way, salt, sodium chloride, you'll see this, I'm not giving away, has a yellow flame, cause the flame to go yellow. Well, which is it? Is the sodium cations or the chloride anions that cause the color? Well, this lab, you're going to find out. Now, when you do experiments, and this is an important lesson I learned, and it was beaten to my head by a couple of my mentors. When you do an experiment, you only change one variable at a time. When you do an experiment, you only change one variable at a time. Well, what variables do we have? Cations and anions. So in part one, you're going to be testing different cations, and you'll be doing this in Beyond Lab Z. I'm going to go there in a little while. And what you'll do is test these different cations in these compounds, but notice the anion is always chloride. So we're only changing in each one of these the cation. And what you'll be asked to do is, I'll show you in a little while, to do the flame test and put down what color you see here. I'll go through this in a while. Now, the other in part B, we're going to do one variable at a time, keep the cation the same, but change different anions. Unfortunately, this is not in Beyond Lab Z, so I have the data for you. If we are in the lab, this is the procedure, like you just saw in the video, you would do. Well, we're not in the lab, so notice I give you the data. And yes, that's correct. They're all yellow. Hint, that should tell you something, which causes the colors. Now, let's go to Beyond Lab Z. All right, that's weird. That's better. All right, thumbs up, people. Everybody see Beyond Lab Z on your screen right now. Thank you. All right, now, what you want to do is in the where it says inorganic on chemistry, click on that. And now you should all see the chemistry lab. Does everybody see that? Where you have the test tube box? All right, now what you're going to do is double click on the test tube box. And notice you have an empty test tube, and this lights up. I'm going to do my favorite. You notice over here, strontium chloride, I'm going to click on that. Notice it now shows me something in the test tube on the right, and the contents, the cation. Now, in the lower left right here, there's a Bunsen burner. We're there, and next to it, flame, it says flame, and flame with cobalt. You don't want to use the flame with cobalt. Cobalt filters out certain colors. I've never used it in my career. A Bunsen burner I have. And what you'll do is click on this. Let's click on the flame. If you notice on the right, the flame is turning a red color. That's how you do it. Now, when you're done with that flame test, in the middle at the bottom where it says clear lab, click on it. I'm going to do another one. These are fun. And, oh, let's do sodium. Now, let's do iron instead. Iron +3. All right, let's do iron +2. I think that's what I have in the lab. And now it's in there. I'm going to click on the Bunsen burner flame. And you see it's white with sparkles. The sparkles aren't that good in real life. The sparkles come out real good. And that's how you do the flame test in Beyond Lab Z. If you notice, I have the instructions how to do that. And notice I have lower, click on the Bunsen burner, and it should be the flame in there, not the Bunsen burner with the cobalt screen. And observe the color. And that's what you do for all of these. I've already done 2 of them for you. And notice you don't always see it, but there'll be sparkles with the ferrochloride, the strontium chloride, SrCl2, Sr +2 or 2+ is red, my favorite color. All right, now in part B, we've already done that. Now, one way of adding energy is with heat. That's what the Bunsen burner does. That's what the explosions, I like that. The explosions, it's corny Tuesday lab time. But anyways, that's what the explosions and the fireworks does. Now there's another way of adding energy, and that's with light, and a specific type of light, ultraviolet radiation, which is higher energy than the visible light that you can see me in. How do you do that? Well, if we're in the lab, we have an ultraviolet light that you can shine on things. Now, this part I did myself, and I took glow-in-the-dark paint, how does that work? Well, it absorbs the regular light, or if you want to do a quicker, ultraviolet light, and that caused the electrons to go to a higher shell. Now, with that, they come back slower rate. So you see that glow for a long time. Now, in this lab, this part, oh, by the way, I forgot part D. There are a couple unknowns. You don't do this in Beyond Lab Z, but if we were in the lab, I'd have 2 bottles unknowns and cleverly labeled unknown A and unknown B. And unknown A, when you do it, it's white with sparkles. Unknown B is red. And later on, the questions I'll ask you, what's the identity of unknown A and B? It's in your table, first table, part A. One of those is A, one of those is B. And by this color, you can tell which is which. Now, glow-in-the-dark paste, how does it work? Well, electrons moving from shells to shell. And this one, you'll determine if there's a difference in how long the colored glow-in-the-dark planes continue to glow in the dark. Now, they don't have this set up in Beyond Lab Z. I've been trying to sell it to them. They've been cheap and haven't done it. Come back to me, but maybe they will, maybe they won't. But anyways, I would, if we were face-to-face, you'd get a special card. You all have the same card, but in real life, I have about 20 different cards. Then you place the card under the UV light for 3 seconds, then remove it. And since I can't shut off the lights in the lab, I came up with getting Jewel shopping bags, the brown paper ones. Yes, I still have some. And you measure the time until it stops to glow, and you record that time. Now, since I don't want to, one of them can last up to hours. If it's greater than 3 minutes, that's the cutoff. And here's the data. For area A, which is red, it only lasts 20 seconds. For area B, it's blue, it lasts 2 minutes, but the green one lasts over 3 minutes, a long time longer, and it's cool. They all are. And here are the questions for you to answer. And that's today's lab. It's moving electrons from shell to shell. And you get to do to be on Lab Z Lab. Now, one thing, one of your colleagues was nice enough to share. I'm going to assume, and let me know if you don't have access, that all of you have access to be on Lab Z. For some reason, they were told not to, and they still did. The bookstore were sending out out-of-date access codes. If you still haven't gotten it in, let me know. By the way, the best way to do it is this: contact support@beyondlabz.com, support@beyondlabz.com. Tell them you're from COD, show them your access code, the email, and they'll send you the right one back because they know about the problem. Why the bookstore doing that, I have no idea. But anyways, I hope you enjoyed today's lecture and lab. Have fun with the flame test. It's a lot of fun. If you have any little kids, let them try it too. And with that, I'm done. I'll see you tomorrow. Don't forget, hold on one second. Actually, it's more than 1 second. I'll put that and post it on my bathroom mirror in my upstairs bathroom. I'll remember. And tomorrow, beginning a lecture, be on time. I have a really fun video to show you and a really great Dr. White story from high school, my high school, that some guys did. I don't know who, but with that, gang gesund. Don't forget to wear your mask. If you haven't been vaccinated, get vaccinated. Don't forget also, I'll be next week or two getting my flu shot vaccination. You should too. And with that, gang gesund. Bye.